All right, everybody. Since we are not having a normal class today, I went ahead and made you a video of what our notes would be for today. So first, I'll remind you that you can stop, pause, replay this video as much as you need so that you can understand the lesson today. And of course, I will answer any questions you might have tomorrow. So on this first screen, you will see your answers for your homework from yesterday. So go ahead and pause. Check your answers, check your work. I did put a little of an explanation for number 34 at the end. And again, I will check this in tomorrow to get your points, but here are your answers to go over. Okay, today we are going to continue talking about limits as we are going to for the entire chapter. And today we are going to talk about what it means to be continuous. Okay, here's your definition. It's a little lengthy, but stay with me here. A function is continuous at a number a in its domain if the limit as x approaches a of f of x is equal to f of a. So what does that mean? It means that the limit is the same as the value of the function. And you should know from our work with limits so far that the only way that can happen is if there are no holes or asymptotes or jumps. So this thing must be a smooth curve if it's continuous. If you would please open up your books to page 94, and we are going to look at 3 graphs there. All right, on page 94, I'm looking at the left-hand side. The top graph, which is A, shows a continuous curve. You can see there's no holes, there's no asymptotes, there's no jumps. At A, the limit is f of a. It's the value of the function. In letter B, the limit does not exist at A because you can see that coming from the right and coming from the left, G approaches 2 different values. So not continuous at point A. And letter C, you see a hiccup function. Okay, this is also not continuous. You see how it breaks there. The limit at A is where the hole is, where the L is on the y-axis, where the value is h of A, where the dot is. So those 2 things do not match up, therefore it is not continuous. Okay, so we're going to look at some functions, and you're going to tell me where it is continuous. So over what intervals are there no breaks, no holes, no jumps, no asymptotes? Hopefully, you've seen by now that we're going to have issues where there are domain errors. So looking at number 1 here, we're probably going to want to factor to see what kind of issues we might have. All right, so there are my factors. You will see that the x minus 1s will reduce, and remember what that means. That means there will be a hole where that happens. So that's a hole at x equals 1. And then we'll have an asymptote where the domain error does not reduce out. So in this case, where is this thing continuous? Well, it's continuous everywhere except at my two domain issues, at 1 and -6. Number 2 here. Again, remember, any issues with continuity will happen where the domain has an issue. And if you look at the denominator here, this thing won't factor. It won't ever be 0, so there are no domain issues. So this thing is continuous everywhere. Number 3. If you take a look at this, you might be concerned and realize that this portion right here really means that. And you know that we have issues with square roots when they're negative. Well, are negative numbers in this domain? And the answer is no. So there will be no portion of the graph there. But once the graph begins, everything else is continuous. Okay, so there just will not be any part of the curve where the x's would be negative in this case. But once the curve starts, there are no breaks or holes or asymptotes. There's no other issues. So this thing is also continuous everywhere. Okay, something a little bit different now. I give you a function and I give you a specific value. And the question is, can you define it so that it becomes continuous? So we're going to go ahead and take a look at these functions, and of course we're going to factor because that's what we're doing with all these guys to see what's happening here. And you'll see that these cancel. So now I'm left with that f of x is equal to x minus 3. Well, notice that my domain error canceled out, and that produced a hole. So in order for me to make this thing continuous, I need to fill in the hole. Okay, so the question is, for what value does that hole need to be? Okay, well, if you go ahead and you put the 3 that we're looking at, this guy right here, in, you will see that it would need to be 0 in order to fill in that hole. So you can redefine this function so it is continuous by making it a piecewise. Okay, the first piece, we're just going to keep my function the same. And that's for everything except for 3. So that's for all x's that are not 3. But when x is 3, if I want to fill in that hole, we're going to make it 0. And now you have defined the function. So yes, you changed it. That's exactly what the problem's asking you to do. We've changed it so that the hole is filled in and therefore is continuous. Let's try again. If you were to go ahead and factor this one, it will come out to be, let's see here, 30. We'll go 3 and 10 minus plus, and you'll see we do not reduce out. So at this domain error, you have an asymptote. There's no way for me to fill in an asymptote. Okay, I can't just use a point to fill it in. So there is no way that this can be redefined so that it is continuous. Okay, and one more like this. Again, let's go ahead and factor. We get 2x minus 1 and x minus 1. Look what happens here. We get our domain error to cancel out. So right now, my function is this. There's a hole at 1 because it canceled out. So if I want to redefine it, I got to figure out what value I need my function to be. And if you plug that in, you will get 1. So for my new function, I'm going to redefine it so we fill the hole. The original function is for everything that's not 1. And my new function tells me where to fill in the hole so it is continuous. Okay. Something a little bit different. Hopefully, you should know how to do this already. Find the equation of the tangent line L to the graph of f at the given point. Well, you know if I'm going to write an equation that I need to have a slope. And if I need a slope, I need to find a limit. So I'll go ahead and set this up and work this out, and you can follow along. You will notice here that we've got fractions within fractions. Pretty ugly. So we are going to go ahead and multiply on the top and bottom to eliminate the fraction within a fraction up top. And it will look something like this. Combine your like terms. Take out a negative. And reduce. And then when you go ahead and you plug in your value there, it should give you a slope of negative 1/4. So this is your slope. And now you can use your point slope form to go ahead and find your equation. Y minus y1 equals m times x minus x1. And once you manipulate that, you should get a final answer of that. That is the equation of the tangent line. Okay, so let's do a couple more, and we'll get you some homework here. All right, if f is that, can you redefine it so that it is continuous? So we're going back to the same types of problems we started with. Okay, well, this time there's no reducing, there's no factoring. Right now, this is a hiccup function. This portion is a line, and this is a point. Okay, so there's going to be a hole at -2. Can you fill in the hole at -2? Well, if you're going to do that, you need to fill in the hole so it's consistent with the line. Okay, so when we do this, this value will be -7. So now the hole will fill in, the point will fill in the hole on the line. If we strategically make this true. Okay. Now it's continuous. Okay. All right, so a new function for you, that's a quadratic. Show that this thing is tangent to the graph of f of x and find the point of tangency. Well, if that's my function, I need to show you what the actual line is. So I kind of missed that portion, sorry folks. My line here looks like this. So I have your function here, it's a parabola. Show that this linear function is tangent to the graph and figure out the point where it is tangent. Well, the point of tangency is just where the two things intersect. So if I'm trying to find where the two things intersect, I just got to set them equal. So I'm trying to find the point of tangency here, and we'll set them equal, and it looks like that. Solve this, set it equal to 0, and you will see that this is a quadratic. You factor it, and you see that x is 5. Okay, so the point of tangency is at 5 comma, and it doesn't matter where you plug that in. Okay, you can pick f of x or you can pick the y, and when you plug that in, you should get 15. Okay, so now we need to go ahead and show that this thing is actually tangent. Well, how do I do that? Okay, if it's actually tangent, we can use our definition of a limit to figure out what the slope should be. I'm sorry, we know what the slope is, it's 8, and we should be able to use that to show that the x value is actually 5, which we just found here. So we have the limit as x approaches a of f of x minus f of a. Well, I'm trying to prove that a is actually that 5 that we said it is. So we're going to leave the a out right now, all over x minus a. Okay, so let's go ahead and distribute the negative symbol. And let's factor by grouping because we want the x minus a to cancel out. Okay, this portion right here is just the difference of two squares. Then you can take a 2 out of the second group. In fact, a -2 out of the second group, all over x minus a. Well, remember how we reduce here. If I want this bottom to cancel out, everything has to reduce by that. And we're left with x plus a minus 2, and the bottom cancels out. Well, our limit here says that x is approaching a. Well, if x is approaching a, then now we make this substitution. And we have 2a minus 2. Now, this is our representation for slope right now. But from the original problem, you know that the slope is supposed to be 8 from that line. So if you solve this, you'll actually see that a is 5, which is consistent with what we found for our point of intersection, right here. So you just proved that that is in fact tangent through that point. Okay? Last problem for us today. Suppose I have this limit as x approaches radical 2 of f of x equals 3, and I have this other limit that also approaches radical 2 of f times x equals negative radical 2. Show that the limit exists and find the limit of g of x. Well, first of all, I want you to see what's going on here. This is just f of x, and this is f times g of x, and we want to find g of x. So you'll see here that you're given 2 of these pieces, and you want to find the other 2. Well, just to show that it exists, right here, all you have to do is look at it, okay? Does f of x exist? Well, yes, they're telling you that the limit is 3. Does f times g exist? Well, yes, they're telling you it's negative radical 2. Well, if those 2 exist, then this must also exist. So, yes, that exists. Now, how am I going to find the limit of g of x? Well, if you look at what you have here up top, we have that f times g is equal to negative radical 2. And we have that f is equal to 3. Well, if you kind of do some substitution here, if f is 3 and the product is negative radical 2, in order to solve for g, you're just going to divide. If I divide by 3 on both sides, I now have that g is negative radical 2 over 3. This is called the quotient rule, okay? And it's something that we will definitely go into more in depth later, but just a little preview for you. All right, that concludes our notes for today. This is your homework. Please notice that for number 64, it says you need to explain why that is true. So I will be looking for an explanation. Tomorrow when you come into class, I'll check your homework that was due today, and I will also check this homework that I just assigned to you, and we will move on. Thanks, and I hope you had a great day.